harmonic oscillator. Okay, two-body harmonic oscillator. A system of two masses. A system of two masses. A system of two masses bodies connected by a spring. Connected by a spring, so that both are free, both are free to oscillate, simple harmonically along, simple harmonically along the length, of the spring constitutes a two-body harmonic oscillator, or two-body harmonic oscillator, or two-body harmonic oscillator. Examples. A system of two masses or bodies connected by a spring, so that both are free to oscillate simple harmonically along the length of the spring constitutes a two-body harmonic oscillator. Okay, example: diatomic molecules. Diatomic molecules like hydrogen, carbon monoxide, hydrogen chloride, etc. Okay, can oscillate along their respective axes of some symmetry. Electromagnetic forces which couple two atoms in a diatomic molecule act like a tiny and massless spring. Okay. Let us consider general case of two-body oscillator consisting of two masses M1 and M2 connected by a spring. M1 and M2 are connected by a spring. Okay. Spring of force constant C. Force constant C are free to oscillate on a frictionless surface. This surface is frictionless. Two mass M1 and M2 is connected to each other by a spring and is free for oscillate, and that part is frictionless, and the spring constant is C. Okay. And let the normal length of the spring be L. Let the normal length of the spring be L, and at any given instant the coordinate of two ends of the spring be x1 and x2. Okay. Extension of the spring. Extension of the spring x equal to x1 minus x2 minus L, where x is positive. If the spring is stretched. If the x is positive, if the spring is stretched. Okay. And x is 0, if the spring has its normal length. If the spring has its normal length, has its normal length, okay, normal length, and x is negative, if the spring is compressed, if the spring is compressed, spring is compressed, okay. Here we assume x to be positive. The force F exerted by the spring on the two masses are equal in magnitude but opposite in sign. The magnitude of the each being Cx. Okay. Let d square x1 upon dt square be the acceleration of the mass m1. Be the acceleration of mass m1 and d square x2 upon dt square be the acceleration of mass m2, okay. Then m1 d square x1 upon dt square equal to minus cx. That is equation number 1, okay. And m2 d square x2 upon dt square, that is plus cx. That is the equation number 2, okay. Multiplying first by m2 and equation number second by m1. And subtracting we get m1 m2 d square x1 upon dt square minus m1 m2 d square x2 upon dt square. That is minus m2 cx minus m1 cx, okay. And m1 m2 d square upon dt square in bracket x1 minus x2, because m1 m2 d square upon dt square is common. Then in bracket x1 minus x2 is left. Okay. Then equal to minus cx is common. And in bracket m1 plus m2, because cx is present in both m2 cx and m1 cx, okay. Then m1 m2 upon m1 plus m2 and transposing to LHS side. So m1 m2 upon m1 plus m2 d square x1 minus x2 upon dt square, that is minus cx, okay. Now L being a constant, then d square x1 minus x2 upon dt square equal to d square of x upon dt square, okay. Putting m1 m2 upon m1 plus m2 equal to mu, called the reduced masses, called called the reduced mass of the system, okay, being smaller than either of the two mass m1 m2, we have d square x upon dt square equal to minus c by mu into x, okay. Then d square x upon dt square is directly proportional to minus x, and c by mu being constant, okay. Then thus the system oscillates simple harmonically with a time period t. Then time period t equal to 2 pi under root of 1 upon c by mu, that is 2 pi under root of mu upon c, and frequency n equal to 1 by t, that is 1 upon 2 pi under root of c upon mu, okay. This gives the frequency of the oscillation, okay. Thank you.